In this episode, we'll see how to use OpenAI's CLIP model for image classification and image similarity. Now, if you recall, a few months ago, we did an episode on multimodal LLMs for image, sound, and video. And one key part of a multimodal LLM is the modality encoder. And we saw that for images, we tend to use modality encoders built with contrastive learning, and OpenAI's CLIP is one of the most widespread models built like this. So if you look at the notebook, I have a link to the original paper, Learning Transferable Visual Models from Natural Language Supervision. So what we are going to do in this notebook is to very quickly review what OpenAI's CLIP model is, then see how we can do zero-shot classification with that model and how we can do image similarity. And I will end this episode by showing you how you can run that model inside Azure AI Studio. This is a very powerful and versatile environment that Microsoft has put together, and realistically, when you run production workloads, you're very likely to use something like that. So without any further ado, let's get started. Before continuing, I'd really appreciate if you could subscribe to the channel, hit the like button and drop a comment below. This really helps the YouTube algorithm understand who likes this type of content and push it to more people. So let's do a very quick overview of CLIP. If you want more information, look at the multimodal LLM video. But essentially what they did with CLIP, they took a set of images which had some captions, and then they have an image encoder which computes the embedding of each image. They have a text encoder which computes the embedding of each of the labels, and then they compute the dot product between these image embeddings and the text embeddings, and they use contrastive learning to essentially make the image embedding and the text embedding dot product that are related to each other very big, while minimizing the dot product between an image and a label or a caption that's not related to that image. So essentially, this is very powerful because it allows the model not just to learn about a category such as this is a dog versus this is a cat, but it allows it to learn about all the nuances that could be present in those millions of image captions that accompany each of these images. So ideally, there will be a lot of nuance that the model will have learned to capture way beyond fixed arbitrary classes. And this is what allows us to do zero-shot image classification. So to see this in action, we do a few imports and then we pull the model in from HuggingFace, and we also need to pull the preprocessor. The preprocessor is essentially what allows us to prepare the text labels and the images so that they can be fed to CLIP's text encoder and image encoder. So I've already run these, and then here I've got some utility functions to load an image from a URL and to display images. So now for zero-shot classification, I've got here 6 images which I am loading and displaying in a second. So the first 3 of them are all images of Cutty Sark, which is, if you live in London, a very famous historic ship. And you can see that they are images of Cutty Sark in different places and historical moments. And image 3 is not a picture, it's a drawing of Cutty Sark, and it's framed, which is a little bit of a nuance because we will see in a second how the model is able to understand the difference between a picture and a framed picture of something. And then we've got playing cards. These are obviously related to each other. These are funds of playing cards, and this is a box of playing cards. So let's see how to feed one of these images to the model. So the way you would use it, you would pass a list of textual labels that you want to try and classify images into. So here I have a very simple a ship, And then I have something a little bit more nuanced, a photo of a ship in a frame, and then I've got playing cards, and then I've got again the nuance, a fan of playing cards. And this is zero shot because I am not taking, for example, ResNet or an existing model and then fine-tuning it on a data set for looking specifically for a fan of playing cards. Here, I'm just giving the labels, giving a certain image, and then asking the model to classify that image against those labels. So the preprocessor simply does nothing but simply prepares the labels and the image so that they can be fed to the text and image encoder, and you see the outputs here. You've got input IDs with 4 tokenizations of these 4 labels. So again, these are just the tokens. This will be the ID of the start of sentence token probably, and this will be the ID of the end of sentence token, or maybe this one is the ID of the end of sentence token, and then you've got also some padding there. So this is definitely the padding. Now, then you have the pixel values, which is the kind of preparation of the image. You take the image and you transform it into a tensor. So if we take a look at the shape of pixel values, we can see we only gave it one image. It's a color image, so we've got 3 RGB channels, and that's the size of the image. The number of pixels that we are preparing, 224 by 224, is the size of the kind of pictures that the model takes, or the encoder of CLIP takes. Then we can pass this input to the model and look at the logits and pass them through a softmax, and this will show us the following. So you can see that the output of the softmax tells us that the probability that the image 1, this one, belongs to the label or the class a ship is pretty high, because it is. And you see also a higher probability that it belongs to the second label, a photo of a ship in a frame, and it definitely is related to that. But when you look at playing cards and a fan of playing cards, you will see that these are very low numbers. No chance that that image is related to any of those labels. Now, if I were to pass, for example, image 4, which I remind you is the fan of playing cards, and I pass that through the model again, obviously we will see very different probabilities. Now, it's very unlikely that that image is an image of a ship, but much more likely that it's the image of playing cards and a fan of playing cards. Now, if we want to do this a little bit better, we can take the preprocessor and we can pass it all the images. So if you see here, I was just passing one image at a time. There's no reason for that. So let me pass it all the images and then print the resulting probabilities. And you can see here that for each image, we've got the probabilities. And as you are expecting, they do kind of, the output is kind of split into left and right, because obviously the first 3 images have got very low probability of being playing cards and much higher probability of being related to a ship. And in particular, if you look at image 3, it's got a very, very high probability of being a photo of a ship in a frame, which indeed it is. And likewise, if you look at the picture of cards, particularly picture number 6, it's got a very high probability of being a picture of cards or playing cards, but a little bit of a lower probability of being a fan of playing cards, because indeed it's related, but it's not a fan of playing cards. Okay, now we'll see how to use the image encoder of the CLIP model to check the similarity between 2 images. The idea here, if you watched the videos on retrieval augmented generation that I have done a few months ago, the idea is very similar to checking the similarity between two sentences using text embeddings. But this time we will check the similarity between two pictures using the image embeddings produced by the CLIP image encoder. And again, this works because each of those embeddings essentially projects the image into a multi-dimensional vector space, and then we can check how distant in that vector space the two images are. And the idea is that images that cluster together or that are closer will be related to each other, while images that are farther away will be less related to each other. Now, a little note here, because we typically don't compute the Euclidean distance between images, but we compute the so-called cosine similarity. Now, in a nutshell, let's say you've got this image here and this image here. You take the angle between the vectors of the two images, and then you perform or you compute the cosine. And so if you look at how the cosine function works, if the angle is 0, the cosine is at its maximum value of 1, and basically means that it's the same image. There is no distance. They are exactly the same points in the vector space. As the angle becomes wider, the cosine goes down, and so the images are less and less similar. So the idea, if you look at this one, is that as we are increasing this angle, the cosine will go down and the images will be less related. Now, in terms of how to do this in practice, it's pretty simple. We've got the images and we pass them through the preprocessor. In this particular case, we're not using any labels, we're not categorizing images. So if you look at here, we passed some text to pass through the text encoder, but here we're ignoring the text and we'll just take the image through the image encoder. So it's going to prepare just the images, and then we are extracting the pixel values. Again, we're just interested in these, and there is going to be, we're not passing text, so there's not going to be any input IDs. And then we can pass this processed image to the model, so we can call getImageFeatures, and that returns the image embedding. Here I'm doing it for the image 1 and image 4, for example, and the size of this embedding in the vector space is 512. Now, I can compute the cosine similarity of the two embeddings just like this, and it's a pretty low similarity because image 1 is this, and I think image 4 is this one. Now, if I change image 4 to image 2 and recompute the cosine similarity, they should be much closer, and indeed the similarity is much higher. And actually, to prove a point, if I put image 1 here, obviously these are the same vectors in the vector space, so the angle is going to be 0 and the similarity is going to be 1, because again, the cosine of 0 is 1. And that's how the similarity here works. What I'm going to do, I have a function called compute similarity to which we can pass the images, and this will compute the similarity between all images. So let's do that and see what this looks like. Now, as expected, image 1 is, we already saw it, image 1 is the same image, so as image 1, so this is 1, and the diagonal is all 1s because they are the same image. And then, because of how we ordered these images, you'll see that we've got these clusters of similarity here. So this is one, and this is the other one. And then we've got these clusters of images that are completely different. So image 6 is very similar to image 5 and to image 4 and has got nothing to do with image 1, 2, and 3, or much less. So that's how you would use CLIP for comparing images. Now I want to show you how you can use the CLIP model from within Azure AI Studio. Azure AI Studio is very powerful and it allows you to play and deploy a lot of different models and you've got different deployment options. But if we go and take a look at the AI Studio, the model catalog is really big. They have 1,791 models at the time of recording. You've got some commercial models like O1 Preview by OpenAI, but then they've got a lot of the open source models, Meta's Llama, Phi, and all the others, Mixtral, and so on. So let me look for the CLIP model. Now, there are different versions of CLIP. There is the larger version, and then there is the base version, which is the one that we've been using for zero-shot image classification. And then there are ones that we can use for embeddings. Now, here you have to do different deployments, even if it's the same model. If you want to do zero-shot classification of images, you need to deploy the zero-shot image classification version because it exposes a certain API. If you want to use it for image similarity, you are going to need to deploy the version for embeddings. So here I'll just choose the one for zero-shot image classification, and you can see that if you wanted, you could try out the model yourself by loading an example image, a set of labels, and it would run this for you. But what I want to do, I want to deploy this model. Now, to deploy this model, you have to choose a virtual machine that it is going to spin up for you and deploy that model on. And you can see here the cost per hour. Now for this particular one, I think I am going to take something which is pretty cheap, this one over here. And when it's deployed, that machine will have an endpoint name that you can use to interact with your own deployment. Now I click deploy and this is going to take some time to deploy. Make sure, if you're following along, to delete your deployment when you don't need it anymore. Otherwise, that's gonna cost a lot of money.
5 minutes later.
All right, this is now deployed and we can look at the Consume tab for an idea of how this model can be used. They give you sample code in different languages. This is the Python one, and I've simply lifted this and copied it inside the notebook here. So the first thing that you'll notice is that we need to pass the images to the model as base 64, or at least we need to pass the base 64 version of the images to the API, which is then going to convert them in the background. So I have here a simple function to take a URL and give me the base 64 encoded version of that. And now this is the code that they provide. As I said, I simply copy and pasted that, and then here in the input to the model, this is the JSON object that your HTTP request needs to pass to the API. It gets some input data, and then there is, here goes the data, so here goes the base 64 encoded image, and then you've got the different labels you're interested in, and be careful because these are separated by comma. This is not an array of or a list of strings. This is just one string and each label is separated by a comma. So that's the payload to the request. So that's the body of the request which I am encoding. The URL, remember this is an endpoint that we specifically deployed. So the URL comes from here, and so comes from here the key that you need. I've put the key in the secrets of this notebook for me. And then you pass the key as an authorization header. So this is really the most straightforward REST API. So then we make the request and we look at the response. So if we do this, I got the request, and if you at the response, and if you look at the response, you get the probabilities across the categories related to the labels. And of course, because I'm passing a picture of Cathy Sark, as before, there is a very high probability that this is a ship. And these numbers are obviously exactly the same that you saw before here. Now, these are the same numbers, obviously rounded. These are rounded up, and you can see it's the same output. Again, I remind you, if you wanted to use Clip for image embeddings, for image similarity, you would need to do another deployment. Now, the other interesting thing is that you can access the logs of all of these. So you can see exactly what's happening, all of the requests, and all of the potential errors. So this is very good for debugging. And you can also go into the monitoring, which is in preview, but you can see how much this is used, what's the latency and stuff like that. So this makes it very simple to take a model and any of those models that you saw in the model catalog and deploy your own standalone contained instance and to monitor what's happening there. Now, to finish this video, I don't want you to forget to delete the deployment if you don't need it anymore, which is exactly what I'm going to do now.